Hello everyone. In the last lecture, we had a look into the interpretation of gravity data. Toward the end of the last lecture, we had seen this particular slide highlighting the various applications of gravity method. The greatest advantage of gravity method is it is very rapid and it can be carried out on land as well as on the sea and also from air. Though we focused very much on the land part, the same can also be carried out on the surface of the ocean also from air. Right? These are the broad advantages of gravity method. Considering this particular aspect, today we are also monitoring the Earth's gravity from the space, right? Thanks to the twin satellites known as GRACE, which is Gravity Recovery and Climate Change Experiment. This was launched in the year 2002, right, for making detailed measurements of Earth's gravity field. Right. Subsequently, in 2018, GRACE follow-on twin satellites were launched because the life expectancy of the satellite that was launched before was around 10 to 15 years. So, as a follow-up, GRACE follow-on satellites were launched during March 2018. This mission has led to discovery of the gravity and in fact how the gravity helps us to understand the Earth's natural systems. That means today with the advent of these satellites, we are able to measure the variation in the gravity over the entire globe. How this is possible? This is possible because of the two satellites which is shown here, right? And a lot of work has been done by these researchers, right? The following couple of slides are based on the presentation, right, sometime during 2005 on the GRACE mission, right, by these people. Right. The GRACE mission itself was a collaborative initiative between the German Space Agency, NASA, then Japanese Space Agency. These agencies put together have launched this GRACE mission in the year 2002. What is the idea behind this? Right? The concept of this mission is there are two satellites which are GRACE satellites 1 and 2. These satellites orbit the Earth, right? This is the Earth, North Pole and South Pole, and the GRACE satellites orbit the Earth in this fashion, right? This is the equator, North Pole and South Pole, right? The GRACE satellites are orbiting between the poles, so these satellites are polar orbit. They are going around the Earth in the polar orbit, that is between south to north and north to south pole, as I have drawn here, right? And these satellites are powered, solar powered as usual, but they are powered in such a way, right, their altitude is freely changing depending upon the Earth's gravitational pull, right? Am I clear? That means the altitude at which these two satellites orbit the Earth between the poles keep changing depending upon the acceleration due to gravity at that particular place. For example, suppose if you assume this particular body as a dense material here. If you have a dense material here, what will happen to this satellite? The satellite's altitude will get slightly reduced because you have some dense part or denser material buried below the surface. So, due to which acceleration due to gravity above that particular place will be little bit marginally higher, little bit higher. Okay. Due to this reason, the satellite will go slightly down because of additional acceleration due to gravity. When the same satellite passes over a huge water body, here we were supposed to have solid earth up to the ground surface, but we have a deep lake or reservoir. Over there, acceleration due to gravity will be marginally less, because here at this particular place we had rocks which are having high density, whereas here we have only water, right, due to which the gravitational pull exerted will get reduced, due to which the satellite will slightly move upwards, right, over the water bodies. So, over dense formation, this satellite slightly goes down, right, the altitude of the satellite goes down. So, this is what is happening, right, and whatever happens to this satellite, the same also will be experienced by the next satellite too, right. So, the two satellites are launched mainly to corroborate and also to check the readings obtained by first satellite. Is it matching with the second satellite? It should more or less match, because the performance or the job of both the satellite is the same, right. What is their job? They orbit the earth and their altitude is controlled by the acceleration due to gravity. Okay. Thus, these two satellites orbit the earth in such a way their altitude at which they orbit depend upon the earth's acceleration due to gravity. If the acceleration due to gravity at point A is very high, the satellite goes down little bit. At point B, we have only very light material, right. The density of the subsurface is very less. The satellite goes little bit upwards, because acceleration due to gravity exerted by the surface over a place where we have only lighter material is comparatively lesser, due to which the satellite's altitude increases. So, that is what is happening in these two satellites. Then the next job is their precise altitude as well as latitude and longitude are continuously monitored by a set of global positioning satellites which are positioned at a much higher altitude. So, why they are called as global positioning satellites? Unlike the gray satellite, which is orbiting the earth this way, the global positioning satellites, GPS satellites 1, 2, 3 like that, over the surface of the earth there are several satellites which are positioned at the same place. That means they are geosynchronous satellites. Their location does not change with respect to the rotation of the earth. Suppose if a GPS satellite is above you, it will be above you always. That means day or night, as we rotate, these satellites also will rotate at a velocity which corresponds to a geosynchronous position, right. So, at any moment of time, the locations of these gray satellites 1 and 2 will be monitored by at least 4 or 5 global positioning satellites. So, what is the idea now? So, with respect to time, we get to know the latitude, longitude as well as elevation of GRACE satellite 1, GRACE satellite 2. Okay. So, continuously we are able to indirectly sense the acceleration due to gravity at the surface of the earth at different times, right. The GRACE 1 and 2 satellites are this, right. It is actual image of the two satellites GRACE 1 and 2, which are monitored by global positioning satellites, which are at a much higher altitude, right. So, the altitude at which GRACE is orbiting is around 500 kilometers, right. And these two satellites are also has a link to correspond. Okay, there is also a link between that, but the important thing is the altitude at which the GRACE satellite is there indirectly indicates us about the acceleration due to gravity. Okay. So, this was the first mission, then followed by that we have now GRACE follow on, which was launched in May 2018. Right. And here is a close up image picture of the GRACE satellite. Here is the first one. The next one also follows the same route. Idea is to cross check the reading that was given by GRACE satellite 1. Right. What is the advantage of these satellites? With these satellites today, we are able to understand the variation in the groundwater mass, or in other words water mass. That means the altitude of the satellite keep changing. The earth, they orbit at least once a month. The satellite goes over the same place once a month, which means it covers the entire earth. Why? Because they are orbiting in this fashion, right? Polar orbiting satellites, as it orbits at the same axis, the earth is also rotating, due to which the entire earth is covered by these satellites, right. They are able to repeat the measurements approximately once a month, right. So, within such a short span of time, if the altitude at which the satellite passes over the same place changes within a month's time, what is the reason, right? There is some change in the Earth's gravity. The major cause for change in the acceleration due to gravity within a short span of time has to be only because of change in the water mass, right. The rest of the thing may not change, right. Suddenly we are not going to build a huge building, or suddenly we are not going to excavate the earth in 30 days, right. So, in such a short span of time, if there is going to be any change in the mass over a particular region, that is likely to be only because of the change in the water mass. That is what is being made use, right, by these researchers. It is a quite old research published in Nature Geoscience, in which they have come out and said how groundwater is being overexploited over the entire earth, right. And here are the vertical scale indicates the ground level of groundwater depletion. So, how did we understood about this? We understood about this from the GRACE data, right. From the change in the acceleration due to gravity from 2002 until this study, right. For over 10 years, they have seen how the gravity values have varied, using which we found out these are the regions in the world where groundwater is being heavily pumped. That means what would have happened here? As groundwater is being heavily pumped and used, the gravity value, or in other words acceleration due to gravity, would have been continuously decreasing over the period of their study, right. Then similarly, Another study carried out by these researchers, right, Journal of Geophysical Research, published in the Journal of Geophysical Research, indicated how the water mass varied during this period, right? Monthly variation every month during 2003, how the mass distribution varied over the entire earth. So, what is the reason for this? The only reason for such a short term variation in gravity value is attributed to change in the water mass. So, that is the greatest advantage of GRACE mission. That is why it is called as Gravity Recovery and Climate Change Experiment. That means the idea of this mission itself is to understand how the water mass is changing with respect to time. Is it related to climate change? So, it is very nice. The gravity methods today help us to understand how the Earth's climate changes over the entire surface of the Earth. And similarly, if you look at the paper published in Science, indicate how in the Amazon basin in South America, the water balance was changing with respect to time, right? Every month, how there is a change in the mass in Amazon basin. Right? So, here you can see the dark colored red is indicating positive and this is indicating negative, right. Positive means gravity values are increasing, which means the density is increasing, more amount of moisture, more water. When it is turning toward this side, depletion in water. So, we are able to rapidly today understand about the change in the water mass, which is directly related to acceleration due to gravity. However, one lacuna in GRACE mission is, as of now, the resolution is poor, right. We may not be able to pinpoint at this locality what is the change in water mass. We cannot answer. Approximately, it is around 250 square kilometer is considered as 1 pixel, right. So, within that only we are able to understand. Nevertheless, though it is of 250 square kilometer resolution, nevertheless this data help us today to understand how the climate change is affecting our water resources, right. In this study, right, carried out by this researcher published in Nature Climate Change, they came out with how groundwater storage in the world's major aquifers are water bearing formations below the surface of the earth. Right? How water storage, in other words, how groundwater storage is decreasing in major aquifers of arid and semi-arid regions of the world, right. These are the major aquifers in the world. Here too, we can see this blue line is from northwestern India, right. Rajasthan, Punjab region, northwestern part of India has been also studied by them, that is this particular line, right. That means how the water storage is declining. That means what we are trying to do is, look at the scale, we are converting the gravity value which we have measured in terms of equivalent water height. Suppose if the water height goes down by a few centimeters, right, approximately you can see here, right, this is the approximate relation between the geoid and the water, right. So, if the gravity value decrease, right, if so much of decrease, so much of will be the decrease in water table. So, this is how, based on the gravity value from the date on which the mission was launched, 2002 March or April, from within couple of months they started collecting the data that they kept as 0 with respect to that date. The groundwater table is falling down, right. So, this is quite old data, but still the idea now is to understand there is a provision, there is an option for us today to understand how the water balance is changing, how we are able to assess that from the gravity measurements. Right. Then here we are focusing slowly from the world, we are coming down to India. This is the region which was referred in their paper previously. This person also has carried out, this group of people also carried out a similar study to indicate how gravity measurements help us to understand groundwater depletion, especially in northwestern part of India. This is again from 2002 to 2008, how the water balance is, right. That means we are able to come out with how groundwater table is decreasing, that is the solid blue line. The trend line is also indicated. This is the trend, negative trend. Groundwater table is going down. Here, though I am telling you in simple terms, right, the change in gravity is due to change in water mass. So, when we say water mass, it includes water in the atmosphere, water in the biosphere, or water in the surface water bodies like rivers, lakes, and soil moisture, and then groundwater, isn't it? Everything put together is the water mass on the surface of the earth. There are provisions for us, there are different satellites that help us to understand what is the moisture in atmosphere, what is the moisture in soil, right. We are able to get this information from other satellites. So, using that, if you segregate and separate that, the remaining is due to groundwater, right. Especially the surface water bodies can also be, what is the volume of water stored in surface water bodies can also be estimated from satellite data. So, total water mass is equivalent to water in soil, water in the atmosphere, water in surface water bodies plus groundwater. So, if you know everything, then we can determine groundwater storage from GRACE data. That is what these people have done. So, that means directly they have related gravity measurements to groundwater depletion.